These are the notes for Module I, Unit 1, Lesson 3. The topic is forces. The essential question is, how do forces affect motion? By the end of this lesson, you should be able to describe different types of forces and explain the effects force has on motion. The picture of the skydiver here is to illustrate that even though the skydiver is not touching the ground, he is affected by the force of gravity, which is exerted on him by the earth. So some forces are not contact forces. Gravity is an example of a force that can act whether you are touching another object or not. There are 3 learning targets in this lesson. The first is I can explain and give examples of the different types of forces. We'll do that in a table in your notes. The second is I can use the formula F equals ma, where F stands for force, m is mass, and a is acceleration. And the third learning target is I can identify Newton's 3 laws of motion. We'll watch a video in class that covers that information. And then there are 3 vocab words in the lesson. Those terms are force, net force, and inertia. So you want to make sure you have those defined in your notes. And the first thing in the notes asks you to name at least 3 examples of forces in everyday life. In the lesson preview, there's a picture of a foot kicking a soccer ball, and in class we talked about how there's force applied by the foot on the ball, and actually the ball pushes back against your foot when you kick it and applies an equal force in an opposite direction. And pretty much any sport you can think of would include examples of force. A baseball hitting a bat, a racket hitting a tennis ball, even when I ride my horse, there's force between the horse's hooves and the ground. And more surprisingly, when you sit on a chair right now, you are putting force on the chair, and the chair is actually applying force back on your body. And those forces are called normal forces. We'll talk more about those in a minute. You can probably think of a lot more examples of forces in your everyday life, and you should name at least 3 in your notes. Then in that table, the first type of force listed is gravity. Gravity is what happens, or what we call it, when objects are attracted to each other because of their mass. We are really aware of Earth's gravitational force because the Earth is so big, it's so massive. What we don't notice is the gravitational attraction between all objects all the time. There is gravitational attraction between your Chromebook and your desk right now, or between your pencil and your desk, or between your body and the chair. But because those objects are so small and have such little mass compared to the size of the Earth, we don't notice that gravitational pull. One example is an apple falling from a tree. And I use that example because legend has it that Newton came up with the idea of gravity while sitting underneath an apple tree when an apple fell on his head. We don't actually know if that's where he got the idea, but we do know that Newton was the first person to come up with the idea of gravity. The second force in your notes is magnetic force. That's another one you're probably familiar with. Magnets on a fridge would be an example. Magnets work because they have opposite poles. The north pole is one end of the magnet, south pole is the other. Those like poles repel each other. They push each other away. Opposites attract. And you would have noticed this when playing with those magnetic Thomas trains as a kid. You couldn't get the like poles to stick together, but if you turned one of the trains around, then they would stick together and you could drive the trains around the track. Contact forces are forces where objects touch each other, such as pushing a lawnmower. If you don't hold on to the lawnmower and push it in the direction you want it to go, it won't actually head that way. Normal forces are all around us, but we tend not to notice them. A normal force is a push upward on one object that rests on another. So for example, as you sit in your chair right now, gravity is pulling your body down toward the chair. The chair pushes back up against your body, and that's what keeps you seated on the chair. Without normal forces, gravity would just continue pulling you down to the floor or even toward the center of the earth. Balanced forces are forces that are equal in magnitude and size, but opposite in direction. So if you think about a tug of war, you've got 2 teams on opposite sides of the rope pulling in opposite directions, and as long as they're pulling with equal force, the rope doesn't move and the tug of war is a tie. So those forces are balanced. Net force is the total of all forces acting on an object, and net force can be 0. If it's 0, the object doesn't move. If you are trying to push a heavy box, it might take a few people pushing in the same direction to move the box. And so when you add all of that force applied by all of the people together, you get the net force and you get the box to move. But if the net force applied isn't enough, then the box isn't going to move. Then in your notes, you've got some pictures, or one picture that I drew for you to illustrate some forces, and you'll need to draw arrows to show the other. We use arrows to show the direction of a force and the direction the arrow is pointing, and then the bigger the arrow, the bigger the force. So the first picture is zero net force. Two arrows equal in size but opposite in direction. The object wouldn't move. That one's done for you. Then next to that, you've got adding forces. So I drew 3 arrows. They're all about the same size and they're headed in the same direction. So when we add all of those forces together, that gives us the total force in that direction. If the forces are not all in the same direction, then you'll subtract. So the bigger force here on the left, smaller force here on the right, and I would take the bigger force minus the smaller force to get the net force. There's an example of that in your workbook. This would be like 2 unequally balanced tug-of-war teams. The rope is going to move in the direction of the bigger, stronger team. So you would take their force minus the force of the weaker team to get the net force applied to the rope. And then combining force. There's a picture of this in the workbook, and there's an illustration in the digital lesson. If 2 forces are applied to an object in different directions, then the object will move in some combination of those 2. So if one force pushes down here like this arrow, and one to the right here like this arrow, the object will actually move in a combination down and to the right. Then we've got Newton's 3 laws of gravity. The first law tells us that objects at rest stay at rest, and objects in motion stay in motion until acted upon by an outside force, and the word for that is inertia. When you go bowling, that bowling ball will continue rolling down the lane until something stops it. The pins, if they get in the way, would stop the ball, or if you manage to miss the pins and the ball keeps rolling and rolling indefinitely, then friction would stop it, because no surfaces on this earth are perfectly smooth and friction-free. So eventually that would slow the object and bring it to a rest. Or in the air, instead of friction, we call it air resistance. Newton's second law of motion tells us that force is equal to mass times acceleration, or F equals ma. And acceleration due to gravity on Earth's surface is always 9.8 meters per second squared. There are some practice problems in your workbook, and we'll do one here. And then Newton's third law of motion tells us that forces act in pairs. For every action, there's an equal but opposite reaction. At the end of the digital lesson, there's a good question. How can an object move in spite of balanced forces? So as you walk across a surface, your body applies force to the ground pushes back up against you in an equal amount but opposite direction. So how can you still move? Well, the answer is that the action and reaction forces have to be acting on different objects in order for that person to be able to walk. Or when I toss a ball, I apply force to the ball applies force back to my hand, but those action and reaction forces are acting on different things. My force acts on the ball acts back on my hand. If they're on the same object, the object couldn't move. And then a practice problem to use that formula, F equals ma. So how much force is needed to move an object with a mass of 25 kilograms? Well, here's what we would do. F equals m times a, mass times acceleration. So F equals, mass is 25 kilograms, times acceleration due to gravity, 9.8 meters per second squared. And when I do the math, I find that F equals 245, and the unit of measurement for force is newtons. So again, we took mass times acceleration. We were told in the problem that mass was 25 kilograms, and on Earth's surface, acceleration due to gravity is 9.8 meters per second squared. Kilograms times meters per second squared gives us a label of newtons, and that's explained in both the digital lesson and the workbook. Those are the notes for Module I, Unit 1, Lesson 3.